Now forget it. You can bring 3 cheat sheets to your exam. Cheat sheet from exam 1. Don't add anything. You really don't need it. It's just for your confidence boost. Cheat sheet from exam 2, same thing. And then for exam 3, you can write a cheat sheet, one side of A4 page or printer paper. You can write all the methods of like the steps of designing a controller. If there's a formula you can bring, you cannot bring a body plot and show where is GM or PM. That's solution, right? So you can write the steps of find this and that. So it's basically the same thing, but at least don't do the body plot, all right? Same for root locus. If you have to do, plot root locus, what are the steps? What are the equations? But you cannot plot anything like, oh, any 2-pole body, root locus would look like this, A and B as a pole. No, it's not acceptable, all right? And you will give me all 3 of them. Okay. Lectures, I think, is it lecture 24? I think I listed it actually. Let's go over there. What are the content? It is, I think, in here. Yeah. So lecture material 25 to 34. So all the way to the last lecture. Last lecture, at least the concept. You might not see problems from that, but concepts are still the game. Homework number 5, including the interview, and class participation 22 to 29. 29 was the SEI, right? Or not? Okay, then 29 was the last. Okay, I will post homework number 5, a solution. All right. And then 29, I already wrote it. I just have to give you access. I'll do it after the class. The exam will be here April 29 at 4 to 5:45 p.m. If you are SLDS, you already have to schedule, I think. It has to be during exam time. So you cannot take the exam in the morning or after this exam is done. It could start before this exam and within the time, or start later, but still students are at the exam. Okay. For those of you that are with SLDS. Now, go back to the thing before. So on top of everything that is in the lectures, what is this? Nonsense. 35. These are, what's that?
Because we get quite a bit more time to spend.
You'll see. I didn't spend 3 hours to create this, to just tell you yes or not. You have to go through 1 hour of this. All right. So you might get a question that will ask you plot root locus. All right. But since we didn't I didn't give you all the steps, you will find, I will tell you what to find. For example, number of Lockeys, calculate the asymptotes, calculate the centroid. Now, you'll see that I say if the asymptote exists, right? So if the case is the asymptote doesn't exist, then you'll be like, there's no asymptote, because for example, what cases you don't have an asymptote? That would be one of the questions. It could be one of the conceptual questions. In what cases, when you're plotting root locus, you don't have an asymptote? What's that? Yes, everyone has their significant other right there. They don't have to go to the future to find it, right? So if number of poles were greater than number of zeros or the other way around, then you have asymptote, so you have to find this. Hence, you will see if any exist. Centroid, you might not have centroid of asymptote, they might not collide, right? So you don't need to calculate it. You need to understand that. So I might ask, but then the answer will be there's no centroid, or centroid is like at 180 or something like 0, right? Don't look at how many points this question has, then decide oh, I might need to find all of it. So really your understanding is important. Now, for example, for this transfer function, you see that it says the loop transfer function is, so loop transfer function means if this was your G, we are gonna put it in our controller, right? If this is our controller, this is the loop transfer function. This is the part that we plot root locus for. We don't care about the closed loop. So every time you're plotting root locus, it has to be just the loop transfer function, just the open loop. We don't consider the feedback in it. Now, this K is your GC. This is your plant. So if I say loop is GC times G, means that I'm considering that K in it. So you will see K in your equation. If it wasn't given, it was just the plant transfer function, it's just G, you know that you have to consider K before it because the standard form is 1 plus KG equal to 0, right? Which is the denominator if you get the closed loop of that, right? You could get either of those. You need to realize which one is it and put it in the standard form. Now, show poles and zeros on S plane. So how many zeros you have? Do you have? None, 0. How many poles do you have? 3, they're gonna be 3. So now your job is to find them. So bring your calculator. So one is a -2. The other one, so this one is S pole, so -2, and then I think is 1 plus minus J, something like that. Oh, not there. So if that is 1, -1, so you'll be like somewhere here. All right, now calculate the number of Locky. How many Lockies you're gonna have? Three, number of poles, 0, whichever is greater. So it's 3. So so we don't have zeros, right? They're all poles. How many asymptote do you think you're gonna have? 3, because all 3 of these poles have to go find their significant other, right? So we know that there's gonna be 3 asymptote. Now, since there are 2 conjugate, we know that the first 2 conjugate move together. So the last one has to move separately. So we know already how the asymptote looks like, right? The motion of root locus is from pole to 0. So here is from pole to 0. So that's one asymptote. Then you have for the other 2. Now, to know how to draw that, you need to now find the angle of the asymptote and then find the centroid, because these 2 will probably collide, their asymptote. Now go write down the equations, find the angle of asymptote and centroid. Meaning that you have to go back to the lecture, so you know what lecture is it, and then find the values and tell me. Someone calculate and tell me what's VA and PB. PB. I know I'm gonna get 3 of them. All right. So we have 60, 180, 300. So this is that 180, right? And then how do I draw 60 and 180? So it's from the pole. Since my pole here is has imaginary part, the angles is still from the real axis. So 60 from here. And then for this one is 300 or negative 60. So this is the asymptote, is not the log key. So where is the centroid? It will be, this is going to happen at negative 1.5, meaning that these will cross this line. So the centroid is negative 1.5. Now, here you have to guess how to plot it. You know that is going to move along the asymptote, right? So there is going to be a crossover the imaginary axis. We don't know exactly like how it moves, but as long as you can draw something, because we didn't talk about angle of arrival or departure, as long as it looks like something like that, it's not crossing it. So let's say something like that. I'll accept it. So those green lines will be your asymptote, and the direction would be from pole to zero. So things that I need you to show if I ask this question is the number of them going from pole to zero, and direction. You have to put an arrow to show that you're going from a pole to a zero. If there was a pole and zero, clearly you should mark it. They would not cross over each other or itself, and it's going toward next to the asymptote. That's enough. Estimation. All right. I won't give you anything super complicated. Will be something that it's the same line of things, and then you just estimate. So the poles have imaginary part, right? But they are positive and negative, cancel out each other, right? So it's basically the real part of it.
So what if you make this?
Connor solved it.
No, I did it wrong.
Okay, I listened to him. Blame Connor. Whatever that is, because I didn't solve this. I just know how it looks like. So if it's -2, the point is, whatever that value is, if it's -2, God, Connor, you just changed everything. You failed.
It's not negative.
And if someone tells me it's not, okay, I'm gonna do it myself. You guys are useless. Okay, Michael, what is it? Huh? Great. So let's assume it's -4.3, right?
Over 3.
4 divided, so 1.33.
Okay, makes sense. I thought it's 430. So 4/3. Let's take this as if it is. Will be somewhere here. So asymptotes will cross this. And then you'll have this guy, example. I would not listen to the next centroid. That's it. The equation is number of poles minus number of zeros divided by n minus n plus 1, I think. Yes.
How do you get different? I know the 181.
So you find Q, there are 3 Qs, 0, 1, and 2, right? And then you have an equation for it. And then you have 3 Qs. So solve for 0, solve for 1, solve for 2, and then you get. All right, moving on from this. So you will see, what's that?
How did you get like which pole was which pole?
So you have three asymptote, right? One is negative 180, one is 60, one is 300. So the conjugate poles move together, meaning that when you're changing K, those two poles move together. So one is going along this, so they mirror each other. So the only one that doesn't have an asymptote would be the one with 180, the one that's on the far right. 60 and 300, it's like 360, right? So those two move together. And then the other one is 180. We also know, because we know this one has to go to infinity to find a zero. And this will be the asymptote. So we just kind of, this is 180 degree.
So it's like the 16 and 360, they're not like because they were cross.
No, this is 60, this is 300.
But if it's like, say, like if you decided to put it the other way around.
It doesn't matter. As that's why, because you don't have the software, you could choose that one is, well, if you say that's 300, okay, hold on. So they will cross, right? So let's say this one, I want to have time to go over everything, but if this was your 300, this would move this, and this would be 60, this move like that. We don't accept crossing. All right. Well, good question, because that could be like one of the solutions that you have to not choose. All right. The other type of question you might get, plus everything else that we already saw with root locus, the other type of question that you might get is something like this. That's actually very interesting. This might apply to other things of the same nature. So I could give you a Bode plot, ask you the same question, for example. All right. So this says that a unity feedback system has the loop transfer function of that. Again, loop transfer function, it has this controller inside of it. Find the gain and roots when the real part of the complex root are located at -2. So it has complex roots. You know what the real parts are. We are going to find the imaginary part and then say where the poles are. So this is our system, GK. We know what this guy is. All right, now to solve this, so here the question tells us that, hey, you have some information about the poles of this system, the roots of this system, not the poles, the roots of this system. Can you find exactly where it is for a specific value of K? So whenever you hear something that it talks about roots, you're placing basically a pole somewhere, right? What's the first thing that you need to find? Just basically say that we are going to place the pole somewhere that the real part of the poles are -2, right? So where do you start solving this problem? I heard someone said, Julia. So you need to get to where do you see zeta and omega n, but where do we see that? Denominator, which is the characteristic equation. We are not going to specifically use zeta and omega n here, but it could have been the case. So you need to, did you just like, was it like, was lucky? It's like, let's say it is probably characteristic equation. So when we talk about characteristic equation, we have information about roots of our system, right? Where we place the poles, what is omega n and zeta. All of these are the same thing. Now, we can find 1 plus kg equal to 0. This is the characteristic based on, if you remember from root locus, that's how you actually plot root locus. So if I create this, I'm showing you how to find the root of the characteristic equation. A lot of time when I solved in class, I gave you the characteristic equation. You just had to use that. Sometime I can give you the system and controller and ask you to find the characteristic equation, but I'm not telling you I'm looking for a characteristic equation. That's the part you need to know. So if you get the common denominator, you have s times s plus 1 plus k times s plus 2. So for this to be 0, this numerator has to be 0. So s times s plus 1, we don't care about this part. If I open this, like multiply s squared plus s plus ks plus 2k equal to 0. So you can see that s squared plus k plus 1 times s plus 2k. So this is the characteristic equation of this system, right? Now, if you have poles, roots, that they are complex and the real part is at -2, they're gonna look like this. -2 plus minus, let's say a times j, right? How would we get this? S plus 2 plus aj times s plus 2 minus aj. Right? So if you solve from this end, you get to a second order polynomial, and then the root's gonna be this complex value. This is pole placement. You place the pole, created the polynomial. So this will give you s squared plus 4s plus 4 plus a squared equal to 0. Right? So if we place the pole at those specific values, this is our characteristic equation. Now, compared to the system characteristic equation, find values for k and a. So this guy is this, and then this one is this. So we are saying that k plus 1 is 4, thus k is 3. 4 plus a squared is 2k, which is 2 times 3, 6. This gives a to be a square root of 3. So our poles will be at -2 plus minus the square root of 3j when k is 3. Right? K is the gain. So if I choose the gain of my system to be 3, the pole will be placed at the value that I wanted. Yes. No, what are you talking about? What?
The last line of bottom line. 4 plus a squared equals 2k. A equals 6.
That's what I wrote. 2k is 6. Then your book is stupid. Like that? Dang. Cheating from book doesn't help either. Okay. I hope the only problem is math in your final exam. Again, I want you to follow the process. But thank you, Michael. Anyway, this is pole placement method. So I could ask different kind of question, right? It could be a root locus. If the poles are at this point, at this place, what is the value of k? If the poles are on the imaginary axes, what is k? So what is the real part on the imaginary axis? 0. So instead of -2, you put 0. So you just have a j and negative aj, right? So this gives me a lot of ways of designing a question. You have the information. You just need to be able to access to it. Not necessarily, you might not necessarily have seen that question, but you have all the information about it. All right. Any question on this? Yes. Because it tells me for the complex pole, the real part is that they're always conjugate. All right. This is a bit long. I'm gonna go solve this one and then go back. So simpler ones first. We have seen this before, right? I give you a state space system I just wanted to show you this, that from the last two lecture, maybe you will see only this kind of question. All right, so you don't have to spend too much time on that. You have either state space system or transfer function, you convert to state space, and then how do we know if it is controllable or observable? Find what? PC for controllability and PO for observability. And then what is it about that? What's the characteristic of those two matrices? Drew? This Drew?
Find the determinant of that.
Uh-huh.
Not equal to 0, then it's controllable.
Yeah, so if it's not 0, it's controllable. And if it, and for PO, the same thing, right? So if this was 1, 2, 1, form PC, which is B, A times B. So this matrix A times matrix B, find the determinant of PC. You will find that for this one is not equal to 0, so check controllable. For part 2, form PO, this is C and CA. Determinant, if you find it, PO is going to be 0, so this is not observable. So this system is controllable, but not observable. All right, the only thing that will change, maybe I'll give you a transfer function and ask you to find that state space and then go from there. All right, so I will post this like annotated version of all of these. Now, let's read lead lag controller question. I want you to read it. I think it should be a 1-minute read. And I want to know what would be your process of solving this question, solving the problem. All right, let's do 1 minute. So, this is a kind of bigger question, right? So whoever asked this, how long it's a bigger question, right? They might spend more time on this one. There won't be too many repeats, but there will be one. So you have a system. This is an actual system that generates power with a voltaic generator. So you always, you see that you always model the time. Lots of information that you might not use all of them. All right, you need to understand what information from the question is. Once you read it, you will see from those, like the second paragraph thing, it tells you about the behavior of your controller, of your system. Okay, cool. You will see, you will observe that if that happens. But the specification are the gain of the controller and the system has to be greater than 20 dB at omega less than 10, so in lower frequencies. And it has to be less than -20 dB at higher frequency, exactly greater than 1000. All right, so those are important points that we want to get back to. And our phase margin PM has to be greater or equal than 60 degrees. So these are the system requirements. Now, we are being asked to calculate GM, PM, and crossover frequency of the uncompensated system. Now, if you look at the second page, I have given you the body plot of the uncompensated system. So you will see some sort of response that you need to do something to it. Now, here you should show the GM, the PM, crossover frequencies, and calculate their values. All right. So if you calculate the GM and PM, the more you explain things here, the better, because don't put anything like in your head and then just write GM equal to some value. To me, you didn't show your work, you won't get point. You will get point for the process as well as the final solution. So let's say we are trying to find PM, right? PM is when your gain is at 0. So at gain 0, here is omega PC. You find what this value is. If you don't know, you can just guess a number. So this is like, I don't know, 8 times 10 to the power 2. So add 8 times 10 to the power 2 radian per second, right? So you read the frequency. If we read this value, we are gonna get, I'm gonna write here, I think is negative 140 is fine, estimation is fine. So negative 140, negative 180, PM is 40 degrees. So either write degrees or degrees. So at this frequency, which is your omega PC, we found our GM. Now, PM, what is our GM? Infinity, right? Because we don't have any crossover here, infinity. Now, if the case was infinity, well, you can't show anything because it's infinity. Now, if this system is stable or not, this is an open loop system, right? So your PM is greater than 0, your GM is infinity. Now, GM infinity for open loop means that our closed loop system is going to be very stable. Doesn't matter what K you design, your closed loop system will be stable. So we will write that the closed loop system is stable, right? So that's the stability question. So answer this, so you're justifying your reasoning because PM greater than 0 and GM for any K, the closed loop system is stable, all right? Now, the other question, determine the proper type of controller for this problem, justify your control selection. Now we need to see the behavior. We know at 10 radian per second and 1000 radian per second, we have some requirement. Let's go and check that. So at 10, which is here, 10 radian per second, this is our magnitude. This has to be greater than, below this has to be greater than 20 dB. For the values below this, check, is greater than 20 dB. Now, the second one, it says that for the frequencies greater than 1000, the gains has to be less than negative 20 dB. So if this is 1000, here's the gain. Well, it looks like we are negative 10, right? So we see that this is not met. We have to shift our body plot 10 dB up, right? So this is one of the problems needs to be fixed. Down, sorry, has to go here. The body plot should be here. So all of the gain above 10 to the power of 3 are below negative 20 dB. So that's one thing needs to be fixed. The second thing that needs to be fixed is what? We have a requirement for PM greater than 60. We just calculated PM and it was 40. So we have some PM that we need to fix and address. Now, what kind of controller would you design that addresses these two problems? Huh? So when you have phase requirement, what kind of controller would you design? So these are from the question that was due on Friday, on Monday, the code thing that I asked you to read the lecture, write the script. So you have to actually read the lecture, follow the steps I did to understand how that was done. So whenever you're asked to design a controller that compensate or meet a requirement for phase margin, you design. Alexis? Yeah, like 50%, just go, think about what lead does, think about what lag does, so eliminate one of them. Adrian. Who actually had a discussion? Okay, you did have a discussion.
Yep.
What is it? Did you remember from last week?
Yeah.
Our conversation?
Lag.
Lead, okay. 50% chance
No.
of being right. So lag controller has a pole close to imaginary axis, right? That's good. It acts like an integrator, so it's good for getting rid of the steady state error. Lead controller makes your system more stable, has a pull on the farther part, adds damping, also helps phase margin. It's basically the advantage of designing lead. You need to study the lecture. You need to read those things. They're all there. I put designing lead and lag, and it's colored in red. All right, so we have phase margin specification lead. We also have to move our body part, right? So that's gain. So we have to design a phase, a lead controller with some gain. All right? Since we have infinity for our gain margin, we can literally choose any gain. The system will be stable. But then we'll say that, okay, we probably need a larger gain. You can't just guess a number. It's like, okay, 100. It's acceptable as long as you say, I need to get over 10 dB. I'm going to design. If I had a software, I would probably give it value. I don't have, but I know that I have to compensate for this 10 dB. And then, what is your current PM 40? What is PM desired? 60. How much you need to compensate? 20. So your fee max is 20. Now, if you read the lecture when you were doing the example for Monday, you saw that you can always add 5 to 10 degree extra to it to just make sure that you're definitely going to reach that because it's greater and equal to 60. So we would add some value, like some degree, like plus 10 for compensation. So phi max is 30 degrees. From this, you find alpha, which is the relation between pole and 0, greater than 1, whatever alpha is. Choose a value for pole and 0. That as if you find the ratio is alpha, is acceptable. Then form your lead controller. Ooh. So your lead controller is going to be, so your GC is some K value times S plus Z, S plus P. Very rudimental. If you want to follow, it's actually 1 over tau plus 1. That is also acceptable. So you have to go to the lecture, either use the formula or this still works because the relationship of S and P, just not in the low pass filter kind of form. Make sense? So again, well, you have all this information. Can you find it across all the lectures? Do you remember like how to access those information? All right. So there will be a question that kind of will ask about everything, you know. Could be like that, could be like a PID control design. I don't know. I haven't actually written your exam yet, but this is another kind of question. I gave you the plan, says load. I kind of gave you what kind of controller I want. I might ask you to design it. Here you have a KA amplifier. You want to find the values for your amplifier that meet some requirement. You basically have to write what your controller is. And then here, for example, I've plotted your time response for 3 values of KA. My question is, label which one is which and choose which KA is desirable based on the specification that you have. Right? So if you had access to MATLAB, you would do all of it, but You don't have, but you still have to do the human part of it. I'm gonna ask you about the human part of it. Make sense? So, for example, for this one, that you have to leave. There are 3K, 20, 40, 60. And then you will find a relationship that has KA in it, and you write the closed loop for that. And then from actually equation, you would know, and then you pick one of them. Now, Brett has something to tell you.
Oh, yeah, so I just created a survey, it's for extra credit, it's, so 5 bonus points to your classification. So the submissions for this are anonymous. I did this a couple of semesters ago when I was a PA for robotics, just like to, get some feedback from all of you, this guy can improve. See it in there, in Carmen now, so extra credit PA survey, it shouldn't take more than 2-3 minutes, so.
So you have until Monday class time. So there's no class on Monday, but this is kind of, is extra credit for you, so it wouldn't cost you anything if you didn't do it. Did you put it here? I will add it in here. I will add it under. What is it? What is it? Okay, it's in the quiz. Yeah, if you have to leave, you can, otherwise I can bring it up and here. So it will be part of your week 16, all right?